Let's do another example here of calculating segment angles and joint angles, and this time we will do the foot and the ankle, which we left out last time. So here I have on my little drawing program here the coordinates of markers on the knee and the ankle, just like we had last time. And this time I've also given coordinate data for the heel and for the toe. If you're interested, the program that I'm using here is a Mac program called OmniGraffle. I don't know if there's a Windows version, but it's a Mac program that I've been using for a lot of years. It's really nice for making nice looking drawings and diagrams. I use it a lot for lectures and slides and stuff like that. And I don't write lab reports anymore, but you guys might find something like this really useful for making nice drawings and nice diagrams for lab reports. There is a free version that I haven't used for a while. I've had the paid version here for a number of years. There is a free version that I think is fairly fully featured, but if you want the full access to like all the features, you have to pay a registration fee. But I think even the free version gives you some nice features for drawing and stuff like that. So if you're looking for a program that does nice kind of diagrams and drawings like this, OmniGraph, will consider giving it a look. I've gotten a lot of mileage out of this program. Okay, so we've got our markers here. Now let's draw our stick figure. So we will connect our, we don't want that to be dashed, I want it to be solid. So we'll draw our shank there and our foot here. Okay, so my shank is again going to be from my knee to my ankle, or between my knee and my ankle, just like last time. The foot is a little more complicated, right? The foot is not just one line like our other body segments. The foot here is this junction of 3 lines. And which one is the long axis? Remember, we define our segment angles as the angle between the right horizontal and the long axis of the body segment. Typically, for the foot, we think of the long axis as running through like the entire mass of the foot. And so typically we define that long axis as being between the heel and the toe as kind of the endpoints of the foot there. We don't, for example, often use like the ankle to the toe because the ankle kind of starts in the midst of the foot. We'd be missing everything behind the ankle. So typically our long axis for the foot will be between the heel and the toe here. So this kind of thicker line that I'm highlighting there to remind us that this is the long axis of the foot that we're dealing with. Okay, just like last time, I define my segment angles by going to the second joint of the segment, which is the ankle in the case of my shank, and drawing a line straight out to the right, my global horizontal axis there, and then the angle swept out between that axis, counterclockwise, back up until I run into the segment. That would be my segment angle, in this case the shank segment angle. Okay. Similar story for the foot. I go to my second joint, or my second point, defining that segment, which in this case is the toe. And I draw the horizontal axis straight out to the right. And then my segment angle here would be the angle subtended, or the angle swept out there between that horizontal axis and this long axis here of the foot. So notice here when I was sweeping out that angle, I kept going here through the top of the foot until I ran in to that long axis of the foot there. So that's the angle there that I'm looking to calculate. Okay, notice I also gave you the coordinates for these markers, the data that you would have if you actually like did an experiment here and measured these coordinates. And so each of these is the x, y position of these markers in the global reference frame here in the page of the screen. And so let's use those data here to actually calculate the segment angles. And so I've got them here in Excel, the XY coordinates of each of those markers. And then my segment angles will be calculated just like they were last time. My shank segment angle is inverse tangent of the y for the ankle minus the y for the knee, divided by x for the ankle minus x for the knee. Gives me negative 1.5-ish radians. Take that times 180 over pi, and that gets me degrees. And remember here, because I got a negative clockwise angle here for my segment angle, I want to add 180 to that to turn it into the positive counterclockwise version of that angle there. So about 94 degrees for my shank angle. Let's go back to our diagram and see if we pass the reality check there. Does that angle look like it's about 94 degrees? Yeah, it's inclined a little bit further back or a little bit more counterclockwise from straight up right relative to the right horizontal here. So 94 degrees seems like it's a plausible angle for that position there of that segment. Okay, as an aside, just to prove to you that point that I was making last time, where the order of doing these subtractions doesn't matter. Here I did, if you look at the top of the bar there, C3 minus C2, which was ankle minus knee. And I got negative 1.5 and got 94-ish degrees overall. This time, let's do knee minus ankle and see if I'm correct there in what I'm saying about the order not mattering. So notice here I did knee minus ankle instead of ankle minus knee. And then on the bottom, I also need to divide by the difference in x positions, knee minus ankle instead of ankle minus knee. And there I still get that same result, right? I still got the 94 degrees that I got last time. So it doesn't matter if you do knee minus ankle or ankle minus knee, as long as you do them both in that order in the numerator and the denominator of calculating that angle. Okay, what about the new piece here? What about the foot? That's going to be inverse tangent of y for the second joint, which is the toe, minus y for the first joint. Heel's not really a joint, but it's the starting point of our long axis. So minus y for that one, divided by difference in x coordinates for the toe, minus x for the heel. Okay, take that times 180 divided by pi, and we get about 5 degrees. Okay, and let's go do our reality check here. Okay, foot is a little funny because does the angle swept out from this horizontal all the way back to this thick black line, does that look like 4 degrees? Definitely not, right? That's way bigger than 4 degrees. It looks like it's like 180 plus a little bit more. So we should be getting something quite a bit bigger there than 4 or 5 degrees. This is another case where Excel is trying to help me and is not really helping me. What it's doing is it's saying, oh, I think you want, if I draw another line here, it's saying, I think you want this little angle in here. And that's not what I want, right? What I want is this big angle here, okay? Because of geometry, this little angle here is the same as the angle swept out if I draw another horizontal back to this side. And you see this little angle there, that angle and this angle are the same angle. They have the same value. Okay? So I can get the angle that I want, this whole foot angle swept out from the right horizontal all the way back to the foot itself. I can again get that here by adding 180 degrees to my foot angle. Okay, so this gets a little different for the foot. The foot's always kind of weird in kinematics of the lower limb. It's just kind of plays by a different set of rules. Notice last time I told you if you get a negative segment angle, add 180 to it. Here I got a positive segment angle, and I still added 180 to it. That's just something that we do for the foot because it has this kind of weird orientation where it's kind of oriented sideways, whereas the other segments here are more oriented straight up and down. So for the foot, generally we add 180 degrees regardless of what value we get for it. For the other segment angles, you just add 180 only when you get a negative for it. You guys don't need to memorize these things. There's not going to be questions on the test that are like, which angles do you add 180 to and which ones don't you add them to? You should remember this part, like you add 180 to it for things other than the foot. But I'm not gonna I'm not gonna have you like try and dredge that up as like a fact on an exam or anything like that. It's just a point of practice here for doing these sorts of calculations. But don't worry about it if you're like not strictly memorizing like, oh, when do I do this? When do I not do this? It's just a step that's involved in performing these calculations. It's not something that you need to memorize in terms of doing it without a reminder or without assistance on exams. Okay, so I've got my segment angles here. Now I can calculate my joint angles. And for the ankle, that is the angle of the foot minus the angle of the shank. And that gets me an angle of 91 degrees there. But remember, for the foot, we had this extra bit here. Or sorry, for the ankle, we had this extra bit here in our joint angle equation. We take the foot angle and we subtract the shank angle, and then we also subtract pi over 2 radians off of it, which is a pi over 2 radians is equal to 90 degrees. So we're not quite done here. I need to subtract 90 from there, and I get a result of about 1 degree for my ankle angle. Okay? What that should say, or what my check here can be, should be, is the angle between this line, let's extend that down a little bit further, the angle between that line and this line, is that equal to a little bit more than 90 degrees, just a tiny bit more than 90 degrees. Well, maybe 1 degree exactly, or just about 1 degree exactly here. 1 degree exactly bigger than 90 degrees. Yeah, it looks pretty close, right? That's just about a right angle there. Not quite, it might be a little bit bigger than a right angle, but it's pretty close to a 90-degree angle there, maybe a tiny bit bigger than 90 degrees there. So again, the angle of the joint there, in terms of being the angle between the long axis of the shank and the long axis of the foot here, again, passing our reality check there for is this a plausible answer to get for this sort of thing. Why, again, do we subtract the 90 degrees here for the ankle angle, but we didn't do that for when we were calculating in the previous example, the previous video? We didn't do that when we were calculating the hip angle or the knee angle. Why do we just do it here for this ankle angle? That is because, remember, we're trying to get it so that when I'm in my upright neutral standing posture, all of my joint angles are 0. And I have to subtract that 90 for that goal, because if I orient everything here in my neutral posture, I line everything up there, then my foot makes an angle of 90 degrees with my shank when I'm in my neutral posture here. So if I don't subtract that 90 degrees from my ankle angle calculation, I'll get an ankle angle here of 90 degrees when I'm in my neutral posture. And I don't want that. I want this neutral posture to have an ankle angle of 0 degrees to kind of represent the resting posture, or the standard or default posture of that joint, along with all the other joints when I'm standing upright there. I want all those to be 0. It's just kind of a point of reference for what it means when you get a value of 0 for joint angles. And so that's why we subtract 90 degrees there from the ankle, but we didn't do that when we were calculating the angles of the hip or of the knee. We just do that for the ankle so that we get 0 for all of our joints when we're in our upright neutral posture here. Okay, that is it for this one. We will see you next time.